Hi everyone, welcome back. In this section we're going to introduce the dot product for two vectors. So we're going to start with a concrete problem. We want to find the angle between these two vectors. So let's get a sketch for what these vectors look like. So our first vector A has x component, our first component 3. It has a 0 for the y component and a 4. 1, 2, 3, 4 for the z component. So there is the corresponding point 3, 0, 4, and we're looking at A as the position vector for that point. So there's our vector A in the diagram. And we've also got this vector B. So B has components 0, 4, and 3. So 1, 2, 3, 4, and 3 along the z-axis. So we can draw it as the position vector for that point, 0, 4, 3. So that's our vector B. And what we are interested in is the angle between these two vectors. What is the angle between them? Now with 3 dimensions, sometimes it's difficult to get your head around as to what the angle between two vectors are in order to just imagine how would I envision this angle. So let's just look at a demo. So here I've got the two vectors drawn. There's A and B, and we're interested in the angle between them. So what would the angle between them be? Well, the idea is that these two vectors, they form a plane. And so if we look at the plane that they both live in, then now it makes sense to talk about the angle between them in terms of it's just the angle between the two line segments in this plane. So it would be that angle there. So that is the angle we are interested in finding. I'm just looking at it from a few different angles, a few different viewpoints. So that's the angle we are interested in finding, the angle between vector A and vector B. So how can we do this? Well, that's going to be our concrete motivating problem for this section. We'll come back to this problem in just a second. I'm now going to introduce the dot product of two vectors, and it turns out that the dot product is connected to the angle between two vectors, as we will see. So here's the definition of the dot product of two vectors. So what is a dot product? It's just a way of taking two vectors as inputs and then combining them together in some way to produce, in this case, a scalar. So we call this the dot product. It's also known as the scalar product of these two vectors. So what is the dot product? It's defined to be just the product of their corresponding components added together. So it's the product of their first components, A1 and B1, plus the product of their second components, A2, B2, plus the product of their third components, A3 and B3. You can also see how then this could drop down to a dot product of two-dimensional vectors. We just multiply their corresponding components and add them up. In this case, it would be A1, B1, plus A2, B2. Or we could extend this dot product to higher dimensional vectors by just continuing on multiplying corresponding components and adding them up. So here's the definition for the dot product for three-dimensional vectors, but it can be applied to any number of dimensions. So let's just do a quick example where we compute a dot product. So we'll take the dot product of A and B, and for that we just multiply their corresponding components. The first component of A is 5, that's times negative 3, which is the first component of B, and then we get the 7 times 4 plus the 0 times 2, and so that's negative 15 plus 28, and then there's a 0 there, and so that's a value of 13. So that's a calculation of a dot product. That's the definition of the dot product, and also in this case an example of how to calculate it. Now one question you may ask is, what does the number 13 actually mean? We get a product of 13. What does that actually mean? In terms of the original two vectors, what is this value that comes out? What does it tell us about the original two vectors? And that's what we're going to get into and explore in this section. So first we will list a few properties of the dot product. The properties of the dot product just follow straight from the definition. So if we look at taking a vector and dotting it with itself, basically we are just summing up the squares of each of its components. And that's precisely the definition of the square of the length. So we get that first property pretty much just by thinking about what we do for the dot product and what we do to compute a length. A dot B is the same as B dot A, so it doesn't matter which order you take the dot product of two vectors in, you'll get the same result. So in our example above, if you were to take B dot A, all that would happen is in each of the products, these values would just switch spots. And because multiplication is commutative, it doesn't matter if you multiply two numbers. For example, 5 times -3 is the same as -3 times 5. So order doesn't matter there, and that trickles on through to tell me that in the order of the vectors in the dot product doesn't matter. The third property is that if we dot A with a sum of vectors, we can dot it with the individual vectors and add them up. This is a distributive property. So I'll write this down, distributive property. This tells us how a dot product distributes over a sum. Property number 4 is that if we scalar multiply a vector and then dot it with another one, that scalar could really float around and be put anywhere. We could take the dot product of the two vectors first, then multiply by the scalar, or we could have multiplied the vector b by the scalar and then dotted it with a. And the last property is if you dot any vector with the 0 vector, you get the 0 scalar. You get 0. So those are properties of the dot product. Now they may not look very surprising, they really just follow from the definition, but the power comes in as to what you can do with them. And so now we're going to use those results to prove this geometric interpretation of the dot product. This is the connection. The dot product is connected with the angle between the two vectors. And that's what we're going to show now. So if theta is the angle between the two vectors a and b, then the dot product is equal to the magnitude of the two vectors multiplied together times cosine of the angle between those two vectors. Let's go ahead and prove that this is the case. So maybe I'll write down here, proof. Now the way we're going to show it, the way we're going to justify this, is we're going to use the law of cosines. And if you don't remember what the law of cosines is, the law of cosines is really just a generalization of the Pythagorean theorem. So relating the lengths of three sides of a triangle, but in this case the triangle doesn't necessarily have to be a right triangle. It doesn't have to contain a right angle. So here's our picture that we're going to look at. We got our vector A, we've got our vector B, we've got the angle between them that we're interested in finding. That alone doesn't make a triangle, but we can introduce a third side to this. The third side I'll introduce it as a vector, and it's the vector b minus a. And so now I've got this triangle, and I can use the law of cosines to relate the lengths of the sides of this triangle. So by the law of cosines, what do we have? Well, it's the length of the side opposite the angle that we are interested in. So that's the length of the side opposite the angle. Actually, it's a square of the length of the side opposite the angle is equal to the sums of the squares of the two side lengths adjacent to the angle. So this is really the Pythagorean theorem if theta was a right angle. But since theta is not necessarily a right angle, we can't assume it. We're interested in finding theta, whatever it is. Then there's this adjustment factor, and this is the law of cosines adjustment factor from the Pythagorean theorem. 2 times, so minus 2 times the length of those two sides adjacent to the angle. So 2 times the length of A, length of B, cosine of the angle between them. So that's the law of cosines. And that gives us a relationship between the lengths of the sides of this triangle and the angle, this one angle theta. So now let's unpack this. We're going to use the properties above to relate the dot product to the lengths. So I've got a length of b minus a all squared. Well, that's just b minus a dotted with itself. So dot b minus a. And then I've got the length of a squared plus the length of b squared minus 2 times the length of a, length of b cosine of theta. All right, now we're going to work out the dot product. We're going to use the distributive property. If I think of this as a single vector, I can distribute it across there. So that would be b minus a dot b minus b minus a dot a. So that's a first application of the distributive property. And then I'll just fill in the right-hand side. And then again, we're going to use a distributive property. In this case, I'm going to distribute this b across that difference. And you may say, well, we don't have a distributive property that lists that we can distribute across from the right. And the idea is, well, we do. You just have to realize that it's a combination of that one and that one. So this becomes b dot b minus a dot b minus b dot a, and then plus a dot a. And that's equal to the magnitude of a squared plus the magnitude of b squared minus 2 the magnitude of a magnitude of b cosine of theta. And now what do we get? Well, a dot a, that's the magnitude of a all squared, so that would cancel with that. And then I also have b dot b. Well, that's just the magnitude of b squared, and that's appearing on the right-hand side, so those would cancel. And then I have a b dot a and an a dot b, but those are the same. Those are both equal to a dot b, and there's negative 2 of them on that side. So this boils down to negative 2 a dot b is equal to negative 2, the length of a, length of b, cosine of theta. And now I can cancel off the negative 2's from each side, and I get a dot b is equal to the magnitude of a, magnitude of b, cosine of theta. And that's what we wanted to prove. The dot product of two vectors is exactly the length of the two vectors multiplied to each other times the cosine of the angle between them. So to answer our question from before, I computed the dot product of these two vectors up above. I got an answer of 13. What does that 13 represent? Well, that's the magnitude of a times the magnitude of b times cosine of the angle between them. So if I divided 13 by the length of a and the length of b, then what I end up with is just cosine of the angle between them. And so that allows me to compute the angle between them. All right. So from that geometric interpretation, if we divide both sides by the length of a and length of b, what we get is cosine of theta is the dot product of a and b divided by the product of their lengths. So let's go ahead and use this result to find the angle between a and b. The cosine of that angle is the dot product of a and b divided by their lengths. The dot product of them is 3 times 0, which is 0, plus 0 times 4, which is 0, plus 4 times 3, which is 12, divided by the length of a, which is square root of 9 plus 16, and the length of b, which is the square root of 16 plus 9. And so that's 12 over root 25 times root 25, or 25. So we have that theta is equal to arc cosine, or cos inverse, however you like to say it, of 12 over 25. So there's the angle between them. If you wanted to get an estimate for, an approximate value for this, you can use a calculator or computer to go ahead and work out some decimal approximation. All right. What else do we get from this formula for the angle between two vectors involving the dot product? Well, what we get is that if we have two non-zero vectors, so two non-zero vectors, they are perpendicular if and only if their dot product is 0. So why is that the case? Well, they're perpendicular, so we use this little upside down t to read perpendicular, so a is perpendicular to b, if and only if the angle between them is pi by 2. So we're using radian measure here. If you wanted to use degrees, the angle between them would be 90 degrees. So they're perpendicular if the angle between them is 90 degrees, or pi by 2 radians. but that happens precisely when cosine of the angle between them is 0, and that's because when we talk about the angle between two vectors, it's a value between 0 and pi. So the only value between 0 and pi that has a cosine of 0 is precisely pi by 2. So they're perpendicular precisely when cosine of the angle between them is 0, and since the two vectors are non-zero, then that happens precisely when the length of A times the length of B times cosine of the angle between them is 0, and that is precisely the dot product. And so I read my implications from start to finish, and I get that the two vectors are perpendicular precisely when their dot product is 0. So that's a nice way to check whether two vectors are perpendicular. Or another way to phrase this is a condition that two vectors have to satisfy in order to be perpendicular, and we're going to use this over and over again. So let's just try it for our first example. Let's check, are A and B perpendicular? Well, we take their dot product, and we get 3 times 2, which is 6, minus 16, plus 10. Oh, that's 16 minus 16, or 0, so the answer is yes. A is perpendicular to B. Now the last thing I want to introduce when talking about the dot product is this idea of projection. So in this definition we have two kinds of projection, a scalar projection and a vector projection. Rather than go into the individual formulas here, we'll get a feel for what the idea is we're trying to capture. So we've got a vector B, we've got another vector A, and the idea is to take that vector B and break it up into the sum of two vectors. One vector that's parallel to A, and one vector that's perpendicular to A. The vector that's perpendicular to A, I'll just call it W. The one that's parallel to A, since it's parallel to A, we can write it as some C times A for some scalar C. And our goal is to figure out what is the value of this scalar C. So how do we find the value of C? Well, the first thing we do is write down the vector B as this decomposition into these two pieces. It's C times A plus W, where C is some real number and W is a vector perpendicular to A. Now once I've got that decomposition, really that's the whole idea, is I take B and I'm trying to write it in this way. Once I've got it written in this way, I can dot it with the vector A. So we'll dot with the vector A. Why are we dotting it with A? Because I'd like to find the value of C in this expression. And that means I'd like to get rid of W. W is perpendicular to A, so if I dotted it with A, I'd get 0. So I take this equation, I dot the left side with A, I dot the right side with A, and I get the A dot W part. That is 0, because A is perpendicular to W. So that means this boils down to A dot B is equal to, and I can factor out that constant all the way out front. I get an A dot A, but A dot A is just the length of A squared, so this equation can be solved for C, and we get that C is equal to A dot B over the length of A squared. That means then that the component of the vector B that is parallel to A, which we've written here as C times A, we actually know the value of C. This vector is what we call the projection of B in the direction of A, and we've just found that the projection of B in the direction of A, which is C times A, we've now found the value of C. So it's A dot B over the length of A all squared times A. And that's the formula we've given up here. So that's what we've referred to as the definition of the projection. But now I've taken a step back and I've introduced or defined the projection in terms of that diagram, and we verify that this is the formula that gives that particular vector we want. Now there's a couple of things to note with this. The first thing is, do these formulas depend on the length of A? They shouldn't, because if we think about what we're doing, we're just taking B and we are saying, how can I write it as a piece that's in the direction of A? I don't care how long A is, I don't care the length of A, all I care about is the direction of A. So how can I write B as a piece that points in the direction of A or is parallel to A? And a piece that's perpendicular to A. So it shouldn't depend on the length of A. And it doesn't, because we could rearrange this formula by grouping one of those lengths in the denominator with the A that's in the dot product, and then the other length of A in the denominator we'll group with the vector on the right, and both of these are unit vectors in the direction of A. So these are unit vectors. So the projection of B onto A, it doesn't matter what the length of A is, because we are normalizing them anyway in the formula. So we normalize A, and then we take the dot product of B with the unit vector in the direction of A and multiply that to the unit vector in the direction of A. So this becomes our scalar. This is essentially going to be the length of the part of B that's in the direction of A. Now I don't really want to call it the length, because what if it was negative? So this is a scalar, and as I said, it's in some sense trying to capture the length of the part of B in the direction of A. But let's look a little bit more closely at that. So what is the length of that part there? Well, the length of that would be the magnitude of the projection of B onto A. And if I look at that expression up above, we see that there's a unit vector here, and then we've got this scalar part. And that scalar part is precisely going to be either the length of this vector or negative the length of this vector, because it all depends on the sign of the dot product. So now I've got absolute value signs on there, and this is what we call the component of B in the direction of A. We call it the component of B in the direction A, and that is A dot B over the length of A, and that can be positive or negative. If the component of B parallel to A actually points in the same direction as A, then this is a positive quantity. This component is positive, and in fact it gives us the length of the part of B that points in the direction of A. If it's negative, it just means that the part of B parallel to A is actually pointing in the opposite direction of A. So the thing to observe with this formula here is that this piece, this scalar, is what we call the component of B in the direction of A. And so that's our scalar and our vector projection. Let's have a look at an example where we use this. So find the scalar and vector projection of this vector B onto A. So we'll first look at the scalar projection. So we're going to look for the component of B in the direction of A. That's given by A dot B over the length of A. A dot B, that's given by 6 minus 2 plus 4. And the length of A is given by the square root of 4 plus 1 plus 1. So that is 8 over root 6. So there is our component in the direction of A. And for the projection vector of B in the direction of A, we can work it out as A dot B over the magnitude of A squared times A. Or we could look at it as the component of B in the direction of A times A over the length of A. We'll write it like this: A dot B over the length of A squared. Well, we've already done A dot B, that was 8. The length of A we already computed above, that was root 6, so the square of it would be 6. And then we're multiplying by the vector A, which is 2, 1, 1. And so this becomes 4/3, 2, 1, 1. So what did these calculations tell us? Well, the first thing to note is that when we computed the dot product, the value is positive. So that means B and A have an acute angle between them. So we're looking at something like this. Here's B, and here's A. And we just worked out that vector there, that projection vector, the projection of B onto A. The way we worked it out was we computed that that projection vector is 8/6 times the vector A. So what this tells me is that my picture actually doesn't represent this particular situation, because it's telling me it's 4/3 times the length of A. So really what's happening is A is shorter than the projection vector. And then my projection vector is there, therefore 4/3 the length of it. And so there is my vector A, and my projection vector is 4/3 the length of that. Also, the dot product is positive, meaning that the angle between them is acute. If the dot product was negative, it means that the angle would be obtuse, and what that means is that if I was to write down the component of B that was parallel to the direction of A, it would have to be negative a multiple of A, because that part of B projected down onto A would point in the opposite direction of A, because the angle between them would be obtuse. So those are the kinds of things we can get out of using the dot product, and in particular asking questions about how one vector projects onto another. Alright, that's it for this section. Thanks for watching, and we'll see you again next time.